The goals of this lesson: students will be able to find positive and negative coterminal angles in radians and degrees, find complements and supplements of angles in radians, and use linear and angular speed to describe motion on a circular path. The first thing that you will do in this video is explore coterminal angles. There is a coterminal exploration that has 2 questions in the notes that you should do by going to this website and answering some of the questions. It will allow you to explore coterminal angles. Once you have done that for a couple minutes, return back to the video to learn about coterminal angles. You should have discovered that a coterminal angle are angles that have the same initial and terminal sides. So if this is your coterminal angle, one of the angles can be represented like that and the other like that. To find coterminal angles, we add or subtract multiples of 360 or 2 pi, depending on what your angle measure is in. In the following example, we'll find one positive and one negative angle that is coterminal to the given angles. There are an infinite number of coterminal angles because you can always add or subtract 360 an infinite number of times. However, the most useful coterminal angles are the coterminal angles that are closest to 0 degrees. So if our given angle is 310 and we want to find a positive coterminal angle, we take 310 degrees and we add 360 to it. 310 plus 360, which is 670 degrees. To find a negative coterminal angle, we start with 310 degrees again, and we subtract 360 degrees, which is negative 50 degrees. Now there are more negative and positive coterminal angles, but these are the most useful for purposes that we will do later. Now, negative 800 degrees. We can find another negative angle by just adding 360 degrees to 800. When we do that, we get negative 440 degrees. Why this is in fact a negative coterminal angle. It's not the most useful negative coterminal angle. We would like the one closest to 0 degrees. So if we add 360 degrees again, we get negative 80 degrees. So to answer the question, give one positive and one negative angle that is coterminal, you could say negative 440 degrees or negative 80 degrees. Now we need a positive angle. So we can take our negative 80, which is coterminal negative 800, and add 360. We are now positive, and our answer is 280 degrees. Now do the practice problems on your own. Pause the video. The next slide will contain the answers to practice 1. Here are the answers to practice 1. A couple things to note. While these are the 2 answers that I gave, there are multiple answers. One thing to think about is if you don't want to keep subtracting or adding 360 to get the closest answer to 0 degrees, you can multiply 360 by a multiple. So I multiplied 360 by 5 and then added it to negative 1,501 and got my positive angle to be 299 degrees. There are an infinite number of positive and negatives. The 2 that I have given are closest to 0. To find positive and negative coterminal angles in radians, you want to add or subtract 2 pi. So if I have 17 pi over 6 and I want to find coterminal to that, I'm going to subtract 2 pi. Now if you're going to subtract 2 pi, you need to have a common denominator the same as you started with. So since my common denominator is 6, I'm going to multiply 2 pi by 6 over 6. So I have 17 pi over 6 minus 12 pi over 6, which gives me 5 pi over 6, which is my positive coterminal angle. Now, if I want to find the negative, I want to keep subtracting 2 pi. So 5 pi over 6 minus 12 pi over 6, which is negative 7 pi over 6. So that is my negative coterminal angle. Now, since this one starts negative and my denominator is 4, I need my denominator to be 4 for 2 pi. So 2 pi with a denominator of 4 is 8 pi over 4. So I'm going to take negative 5 pi over 4 and add 8 pi over 4, which results in 3 pi over 4. That's a positive angle in radians, so there's my positive angle. Now I need a negative angle. So since adding 2 pi gave me a positive angle, I need to take my original angle, which is negative 5 pi over 4, and I need to subtract 2 pi, which is 8 pi over 4. So my negative coterminal angle is negative 13 pi over 4. Once again, there are infinite possibilities, but these are the closest angles to 0 radians that are not the angle that was originally given. Now pause the video and complete practice 2. The answers will be on the next slide. Here are types of angles. In previous math classes, you've learned about acute, right, obtuse, straight, and full revolution. In degrees, an acute angle is anything between 0 and 90 degrees, and in radians, it's anything between 0 and pi over 2. A right angle is 90 degrees and pi over 2 radians. An obtuse angle is between 90 degrees and 180 degrees, and in radians between pi over 2 and pi. A straight angle is 180 degrees, or pi, and a full revolution is 360 degrees and 2 pi radians. You'll probably recall from geometry that complementary angles are two positive angles that add up to 90 degrees. In radians, it would be pi over 2. Supplementary angles are positive angles that add up to 180 degrees, or pi in radians. To find the complement and a supplement of an angle, you either subtract from pi over 2 if you're looking for a complement, or subtract from pi if you're looking for a supplement. So since we're trying to find the complement of 2 pi over 5, we'll do pi over 2 minus 2 pi over 5. Now we need a common denominator to subtract these. So our common denominator is 10. So we have 5 pi over 10 minus 4 pi over 10, which is pi over 10. So pi over 10 is the complement of 2 pi over 5. Now remember that in order to be a complement, your angles have to both be positive. So if your complement is negative, then you don't actually have a complement. To find the supplement, we subtract from pi. So pi minus 2 pi over 5. Now to make a common denominator with 5, we need to multiply pi by 5 over 5. So we have 5 pi over 5 minus 2 pi over 5. So our complement, not our complement, our supplement is 3 pi over 5. Now you try to find a complement and a supplement. The answer will be on the next page. The last thing that we will be exploring is linear and angular speed. Angular speed measures how fast the angle changes, and linear speed measures how fast a particle moves. All of these are motions that describe circular motion. So linear speed is arc length divided by time. So if you think about traveling around a circle or a portion of an arc, if you take the length of that arc and divide it by time, you get the linear speed. Angular speed is how fast the angle moves. So you take the angle in radians and divide it by time. How do revolutions in a circle relate to the angle measure in radians? So once around a circle, so one revolution, is 2 pi radians. 2 revolutions is 4 pi radians. 3 revolutions is 6 pi radians. Each time you travel around a circle, the number of revolutions it's the number of revolutions times 2 pi radians. How are revolutions in a circle and arc length in the same circle related? We'll recall from previous lessons that arc length is the radius times theta, where theta is your angle in radians. So if you know the number of revolutions, so suppose it's 2 revolutions. 2 revolutions means the angle is 2 times 2 pi. So our angle, our theta in this situation, would be 4 pi. Now, if our radius was 10 centimeters, the arc length would be 10 centimeters times 4 pi radians. So our arc length would be 40 pi centimeters. So linear speed can be given by a multitude of formulas. So we know that linear speed is your arc length divided by your time. Well, we also know that arc length is the radius times the angle measured in radians. So we can replace that s with r theta. So another formula for linear speed is the radius times theta, which is the angle in radians, divided by time. Now, angular speed, which we use the Greek letter omega, equals theta divided by time. If you notice in the linear speed that also exists theta divided by time, which is the angular speed. So you can also write the linear speed as the radius times the angular speed. There's 3 different ways to represent the linear speed and 1 way to represent the angular speed. We will now do an example of linear speed. Example 4. The second hand of a clock is 10.2 centimeters long as shown. Here's our second hand. The second hand is the hand on the clock that travels all the way around the clock in 1 minute. Find the linear speed of the top of this second hand, the top of this, as it passes around the clock face. Well, we know that linear speed is given by arc length divided by time. And arc length, we know, is the radius times the angle in radians. Now, in this particular situation, our second hand is traveling around a clock, and we know that it makes 1 revolution in 60 seconds. Now, you can represent it as 60 seconds or 1 minute. This particular problem did not say what the units were, so you can use either 60 seconds or 1 minute. Now, since we're traveling 1 revolution, we know 1 revolution is 2 pi radians. So if we want to find our arc length, which is s, is the radius times the angle measured in radians. So in this case, our radius is 10.2 centimeters times our angle, in this case, is 2 pi. So if we want to find our linear speed, we take our arc length, which is 10.2 centimeters times 2 pi, and we divide it by the time. We'll do 1 minute first, and then we'll also do 1 second. So if you put this into your calculator, 10.2 centimeters times 2 pi divided by 1 minute, you get 64.08 centimeters per minute. That's the linear speed in centimeters per minute. You can do the same exact linear speed, but represented in different units, in centimeters per second. So the setup would be the same, 10.2 centimeters times 2 pi divided by 60 seconds. When you plug that into your calculator, you get 1.068 centimeters per second. Both answers are valid and represent the speed of the tip of the second hand as it travels around this particular clock face. This example is going to show angular speed and linear speed. Example 5. The blades of a wind turbine are 116 feet long. The propeller rotates 15 revolutions per minute. Find the angular speed of the propeller in radians per minute. So angular speed, which is our omega, is represented by the angle in radians divided by time. In this situation, we're told that we do 15 revolutions in 1 minute. So our time is going to be 1 minute. Our angle is 15 revolutions, so we know that each revolution is 1 pi, so we take our 15 revolutions and multiply it by 2 pi. So our angle in radians is 30 pi. So if we want to find our angular speed, we take our angle in radians, which is 30 pi, and that's in radians, and we divide it by 1 minute. So 30 pi radians divided by 1 minute is 94.25 radians per minute. To find the linear speed, as we recall, linear speed is arc length divided by time. Or we can think of it as arc length, which is r theta divided by time. Well, an angular speed is the angle divided by time. So right here is our angular speed. So if we take our angular speed and multiply it by the radius, we'll get our linear velocity. So our velocity is radius times angular speed. Anytime you do a problem, you should always go back to the exact answer. So our angular speed, the exact answer, was 30 pi radians per minute. So we're going to take the radius, which is 116 feet, and we're going to multiply it by the angular speed, which is 30 pi radians per minute. And when we multiply that out using our calculator, we get 10,932.7 feet per minute. This is the end of the notes portion. There are numerous examples that you will practice at another time, but this is just a lesson for today.